Our topic today is what's the deal with calcium? And the reason I gave it that title is that's a question I get quite a bit. In fact, this has been going on a long time. People will call me up and ask about calcium and want a very big answer in a very short period of time. I have a textbook, Fundamentals of TURFGRASS Management. It's now in its 5th edition. One of the things that was expanded in the last edition was the session on calcium, because we've done some additional research since the early editions came out. So anything we talk about today you would find in Fundamentals of TURFGRASS Management. All right, so how did this get started? Well, I was getting call after call, and I have a coworker, Adam Tones, who's at Iowa State, and he gets this question quite a bit too. People will call up and they'll usually start out by saying, everybody wants to sell me calcium, okay? And a lot of these calcium supplements are really expensive. Do I need it or not? Now that's kind of a difficult question. That's not a yes/no question. There are so many fine details, so many things you need to know before you can answer that it's something that takes a little bit of thought. And that's where we're going to start today. We're going to start with some of the basics of calcium. Then we're going to talk about some of the research we've done at Iowa State, and then try to answer, do you need calcium or don't you need calcium? Now, there are 17 essential elements that are needed for all plants. This is a group of elements that's recognized by the plant physiologists of the world. They include the obvious ones like carbon, hydrogen, oxygen, N, P, and K, and then there's a whole bunch of minor elements. Calcium is definitely one of these. Calcium is an essential element for all plants. It's involved in a number of physiological processes in the plant that we'll get to here in a little while. And definitely, plants need calcium. Now, do they need additional calcium? That is another question. I'm sure you've heard the terms macronutrients and micronutrients. The macronutrients are the ones that we normally think of, like N, P, and K. Carbon, hydrogen, and oxygen, by the way, are very important too, but they enter the plant in different ways. But N, P, and K are big ones. A lot of times, in fact, if you go to the show later in the week, they will probably be selling calcium in some of the booths, and they will probably count it as a micronutrient. But from a strict definition, calcium is a macronutrient. If you talk to a plant physiologist, they'll tell you that anything found in the plant in 1,000 milligrams per kilogram, or parts per million, or more, is a macronutrient. Now, certainly carbon, hydrogen, oxygen, N, P, and K, but sulfur, magnesium, and calcium are also in that list. So the plant does use quite a bit of calcium. The micronutrients are found in the plant in very, very small quantities, 100 milligrams per kilogram or 100 parts per million or less. And that's molybdenum, copper, zinc, and a lot of these others. And sometimes the question will come in, do I need molybdenum? Do I need zinc? Do I have too much zinc? Those are all very important questions. Okay, let's zero in on calcium. Calcium plays many very important roles in the plant. It is involved in cell wall formation. It's involved in the rigidity of the plant. It's involved in wear tolerance in various ways. It's involved in cell division, another very important part of the growth process. If you don't have enough calcium, the division of the cells is not going to take place the way it should. It plays some very important roles in the plant in osmotic balance, the ability of the plant to take heat stress, drought stress. A lot of these things are related to it. And then finally, from a physiological standpoint, membrane stabilization. There's been a lot of work done on calcium, and definitely plants need calcium, no question about it. What do you see if you have a deficiency in calcium? Okay, anybody ever seen a deficiency in calcium? I'm not going to get many hands on that because it is extremely rare. In fact, I have never seen it myself in the field. You have to generate this in the greenhouse where you grow plants on very low calcium media. You can develop a deficiency symptom. The younger leaves will turn reddish brown, and it fades to kind of a reddish coloration. So if you have a real calcium deficiency, It's not going to be a chlorosis like many of the other elements are. It's going to turn to kind of a red color. Now, you're not going to see this in nature very often because generally we have enough calcium. The plants are going to be getting enough, particularly in higher pH soils. The plants are going to have enough. You're not going to see it. And if you are in an area like the East Coast, where you do have soil media that can be very low in calcium, you might see it there, but you're probably going to lime, and we'll talk about lime later on. It's the process of adding calcium carbonate. You're going to lime long before you see a deficiency in calcium. So we don't see it very often in nature. Where would you expect it? You would expect it in a low pH soil and a low CEC soil. Now, I'm going to explain a lot more about what those two terms mean, but remember that low pH and low CEC. So that's one of the first things when somebody says, well, do I need calcium? I'm going to ask about the chemistry of their soil. Do you have a soil test? I'm going to ask about the pH. I'm going to ask about something called the CEC. Now, this is a concept that is very important to just about everything in life. It is called a curve of diminishing returns. Now, this is something we use a lot in the agronomic field. If we're developing a soil test, what we'll do is go out and find a soil media or create one in the greenhouse sometimes that is very, very low in the element that we're trying to study. And then it's a simple study. You put on increments of it. So let's say you're interested in potassium. Okay, we'll find a soil that's very limited in potassium, and we'll put down 1 pound, 2 pounds, 3 pounds, 4 pounds, and then we'll measure the response. And usually with crops, that's going to be yield, how much corn, how much soybeans am I getting, but we're measuring some kind of response to the plant. And what you find with all of the elements, and this is just a universal concept that's used in developing these soil tests, you get this curve of diminishing returns. If you have a serious deficiency, the plant's not going to function. Okay, you add the first increment of it, like the first pound of potassium, you're going to get a lot back for your money. You're going to get a lot of response. You're really going to see something. The second pound is going to give you something back, but not as much as the first pound. And as you add more and more, you reach this leveling off point here. Okay, and that is at the peak of the curve of diminishing returns. That's what we're interested in. And when they're developing a soil test, they'll go over here, draw the line down, and say, that's how much you need. That's how much potassium, that's how much phosphorus, that's what you need on this particular soil for this particular crop in this particular climate, etc. There's a lot of variables that go into this. But it is a very effective way of doing this. Now, if you've studied other areas, if you've ever taken an economics class, they talk about curves of diminishing returns all the time. If you are putting economic inputs into something, you get a lot back from the first increment, and it gets less and less until it levels off. Think about vitamins, okay? People will ask this. If you ask a nutritionist, do I need vitamin D? Do I need vitamin E? Do I need vitamin C? Well, what they'll tell you is about the curve of diminishing returns. If you have a true deficiency in that, let's say vitamin D, your body's not going to function very well. And you get some vitamin D, and it's a miracle material. I mean, it just turns your life around. However, if you're up here where you have enough of it already, and that's where most of us are, our diet has enough vitamin D and enough vitamin E and so on in it, more and more and more is not going to do you any good. And that's a very important concept thinking of nutrition, and that's particularly important with calcium. So if you have enough calcium, you don't need more calcium is basically going to be the answer. But how much is that? That's another question. Another part of this curve of diminishing returns is you can do harm, okay, if you've got too much. Vitamin D again, and there have been some studies on this recently. People were taking excessive amounts of vitamin D, and if you get too much, you're going to do harm. It's going to trail off, and that's true of many of the nutrients. Not enough, you're going to get a response. Too much, you're going to get a negative response. Way back when I was a grad student, we had a technician at Ohio State University, and on the door of his office, he'd been taking soils courses, and he had a curve of diminishing returns that looked a lot like this. And he had his condition over here and the number of beers consumed over here. And he had what he was saying was, yeah, that first beer, I get a lot out of that. And the second beer helped me a little bit. But you know what happens at 6, 7, and 8 beers? That's not good. So everything kind of falls on this curve of diminishing returns, and it fits so well with so many biological systems, and particularly with plant nutrition, that we use that a lot. And we're gonna come back to that later when we get to the end. Okay, I mentioned that if you're going to run into a calcium deficiency, you're probably going to have a low pH, and I'll get to pH in a minute, and a low CEC soil. Now, what is CEC? Generally, when you get a soil test run, that's going to be one of the first things that's listed on it. It's going to give you CEC, and then it's going to give you pH. And on most soil tests, they don't even explain what that is. In fact, I'll get soil test in, and they don't even tell you that CEC is cation exchange capacity. That's what it stands for. They just say, CEC, here's your number, take it or leave it. So you've got to know how to interpret that, and you've got to know what exactly that means. Now, if you've got a plant science dictionary, or you look it up on the web and say, what is CEC? It'll say it's the ability to exchange cations. Now, if you haven't had a soils background, that's going to be a little like Greek. What's that mean? Okay, what is a cation? What do I care if it's exchanged? What's that mean to me? Okay, so let's start with the cations. The cations are a series of positively charged elements. That plus sign up there is a positive charge that are of interest to us in the soil. So when we're talking about the cations, we're talking about essential nutrient elements in most cases, not all, but we're talking about elements that have a positive charge. Notice that some of these have one positive charge, some have two, and that's important. When we talk about liming later on, the fact that calcium has two and hydrogen has one is going to make a big difference to us. Okay, when you have a single positive charge like hydrogen and potassium here, that is called monovalent. And if you read an article on it where they're talking about this, and by the way, in addition to my textbook, Adam Tomes and myself just finished an article about a week ago on this for Sports Turf. So in the February issue, there'll be an article on today's talk in there. Okay, hydrogen is monovalent. It has one positive charge. Calcium, magnesium are divalent. They have two positive charge. A mono is one, di is two. All right, so let's look at these elements. What are we talking about? Hydrogen, H. It's got a single positive charge. Now, we don't normally think about hydrogen when we think about plant nutrition because the plant doesn't get that from a fertilizer. The plant gets it from water. It gets it from the atmosphere. It's actively involved, though, in its physiological system. It's a very important element to us. As you'll see in a minute, we think a lot about hydrogen. We measure hydrogen, and we use that to interpret what's going on in the soil. But we don't normally think about it as a fertilizer element. Calcium is a cation. It is a divalent cation. It has two positive charges on it, and it's a very important one to plant growth. Another very important one is magnesium. In fact, we could do a similar talk on magnesium. Magnesium is a divalent cation. It plays very important roles in the plant. It's at the center of the chlorophyll molecule. And if you don't have enough magnesium, the plant's going to turn yellow. It's going to get chlorotic, and it's not going to function well. And remember, calcium, that's not the case. Calcium, it's going to get kind of a reddish color. Potassium is one of the big three. NPMK, it is a cation. It has a single positive charge. Plays a lot of very important roles. If you are in an area where you've got a lot of sodium, you're probably going to be testing the sodium in the soil too. Now, that's not an essential element for most plants. It's going to be a problem to you. It's going to damage plants. It can kill plants. And we don't want sodium. We don't want salt water intruding down here in the coastal areas. We don't want storm water from the ocean like they get in Hawaii blowing up on the golf courses. And in our part of the country, we don't normally think a lot about natural sodium in the soil, but we use sodium chloride to melt salt. When I left, we were getting we just had an ice storm. We were getting more snow. I'm from Iowa, and they put sodium chloride out, and that gets on the grass and it causes a lot of problems. Well, sodium is a cation, and it plays some very important roles in the soil, and we'll talk a little bit about those later. Now, the soil has a series of negative electrical charges on it, and that's what these minus signs are. So you've got plus signs on the cations, you've got negative signs on the clay and on the humus. And these act a lot like magnets in the soil. Now, you all played with magnets when you were young, and you know that if you try to push a North Pole and a North Pole together, that don't work. They're going to repel. And if you turn it around, you put a South Pole and a South Pole together, they push away. However, if you get a North Pole close to a South Pole, they're going to bond. And these charges in the soil are like magnets. So when you get a positively charged cation, like calcium, magnesium, potassium, close to the negative electrical signs on the soil, they bond, and they are held in place. And that's what cation exchange is. The cations are held in place on the cation exchange sites, and they can exchange with the root system. The plant needs these elements for growth and development, and they exchange. What do they exchange with? Hydrogen. Hydrogen's going to come back and join on the cation exchange sites. When we measure cation exchange on a soil test, we're measuring the number of these negative signs. How many negative signs are there to hold the cations in place? And that's going to tell us a lot about the fertility of the soil. If I don't have many cation exchange sites, I can't hold a lot of cations in place. If I have a lot of cation exchange sites, I'm probably going to have abundant calcium and magnesium and the other elements. What kind of numbers are we looking at? If you look at a soil test, on the top of the column, it's going to say it's measured in MEQs per 100 Gs. Now, what's that mean? That's milliequivalent, and that's a chemical term. It's actually a very big number. It's 6.02 times 10 to the 20th power. There's 20 zeros out there, so one of these is a lot. It's millions and trillions. But they're very small, and you need a lot of them in the soil. And 100 Gs is 100 grams of soil. There's 454 grams in a pound, and this is about a cup of soil. So how many of these negative sites are in about a cup of soil? And that's going to tell us a lot about the ability of that soil to hold these cations in place. Now, the texture of the soil varies a lot as to the cation exchange capacity. A sand is generally quite low. It's got larger particles in it. It doesn't have many of these negative sites. And a sand is not going to be able to hold many of the cations in place for exchange with the root system. So a sand can have a problem. Soil texture, again, is going to play a big role in this. Do I need calcium? Well, it's going to depend on what you've got. You've got a sand-based system and a very low CEC, like 1 or 2. That means you don't have a lot of these cation exchange sites, and you're probably not going to hold enough calcium in place for exchange. Okay, so sands are quite low. They can be less than 1, particularly new constructed areas, new sand-based fields, new sand-based greens. They'll be 0.5, 0.8 sometimes. In the golf industry, they're building things called California greens where they don't put any peat in them. It's just sand. And they have incredibly low cation exchange capacities. Over time, they'll increase somewhat. You get breakdown of the root system. You get more organic matter in there. You get top dressing and windblown materials. But it's generally going to be quite low if you have a sand. Now, a clay has a very high CEC. Clays are 80 to 120, and you might think, well, that's good. Yeah, I want a clay. I want something with a lot of these negative sites that can hold the calcium and the other elements in place. So I want a clay. No, you don't want a clay because of the physical characteristics of the clays. If you've ever tried to manage a sports field on a clay soil, you know that it doesn't work very well. They don't drain well. You don't get good root growth. You don't have good oxygen down there for the roots. You got a lot of problems with clay. So the number can be too high. You can have too much, and if I see a very high number, that means it's probably a clay soil. Organic matter has a very high CEC per unit weight, 150 to 500. So you get a lot of cation exchange capacity sites with a little bit of organic matter. And that is why when we build sand-based systems, we often put organic matter in it like a peat. The peat's going to boost the cation exchange capacity. It's going to help with water holding. We want the sand because it doesn't compact. It's going to drain well when we get too much rain. But we pay a price when it comes to cation exchange capacity. So a little peat will help. Peat's not going to turn a sand into a clay loam soil, but it helps a lot. Now, I see my numbers kind of jumped here. What are we looking for? What's a good number? When I pick up a soil test, what do I want to see? Well, a good clay loam soil will be about 25 to 30, about 25 to 30. So that's a good number. If you've got 25 to 30, you have plenty of these cation exchange sites to hold the cations in place, and you have most likely have good physical characteristics of that soil. It's going to be a pretty good media for growing turf. It might compact, but it's going to be basically a pretty good media. So 25 to 30 is a good number. Now, a sand green or a sand athletic field is going to start out very low, and like I said, it will go up with time. I did some studies on this a number of years ago. I had a student who went back and on golf courses of various age, went to courses that had a complete list of soil and physical tests when they started, and then we monitored that over time. We had some that were 6 years and 15 years and 19 years, and what you'll see is that the CEC does go up over time, and it does affect the nutrition of the soil a lot, but initially in the grow-in phase it can be very, very low. All right, so that's CEC. Now, how about pH? pH is generally the next number down the list, and again, they'll just say, here's pH. They write it with a little p and a big H, which is very confusing a lot of times. People look at that and say, what the heck is that? And then they give you a number. Okay, that number has a lot of meaning, as you're going to see, and particularly when we put it together with the CEC. The P is potential. It's a mathematical term that is quite complex, but it's basically a measurement of hydrogen. That's what the H is. So when we're measuring pH, we're measuring the hydrogen in the system. Now, we use that term pH and we measure hydrogen in a lot of different living systems. If you've had a physical, they'll measure the pH of your urine and the pH of your blood, and it is a very important concept, and in the soil it's a very important concept to us as well. So we want to know how much hydrogen is in there. Now, interpreting that scale is a little more difficult because it is an inverse scale. It's flipped over. Okay, when you look at the pH scale, it ranges on the left from 0 to 14 on the right, and in the middle is 7, and 7 is called the neutral point. Now, normally you'd think if we're going to develop a system to measure something like CEC, how many of those sites are there, the bigger the number, the more there's going to be. Okay, and normally a system works that way. However, with pH, it's just the opposite. It's an inverse scale, and as you go down the scale, you're getting more and more hydrogen. So as you go from 7 into the lower pHs like 5 and 4, that means that you've got a lot of hydrogen in the system. It's also a logarithmic scale. It's based on a factor of 10. So going from 5 to 6 to 7 is not a matter of just one number, 5 to 6 to 7. It's a matter of 10, and then a matter of 100, and then a matter of 1,000. So it's very difficult to go up and down that scale. You've got a very big change in the amount of hydrogen in that system as you go up and down. Everything below 7 is called acidic, and it means there's a lot of hydrogen on the cation exchange sites. Everything above 7 is called alkaline, or sometimes you'll see the word basic used, and it means that there's other elements on the cation exchange sites. When you see a pH number on the test, this is what should pop up in your mind. It's telling us about the cations on the cation exchange sites. That's why they generally measure CEC. They give you that number, and then they measure pH. Okay, what's your ability to hold the cations, and then what's on those cation exchange sites. Now, as you go down from 7, remember you're getting more and more hydrogen, and what that means is there's hydrogen on those cation exchange sites. And by default, if I have a hydrogen on a cation exchange site, I don't have a calcium, I don't have a magnesium, I don't have a potassium, okay? So I'm going to be deficient in those elements in that low range. Now, as you go up, you've got a lot of calcium, you've got a lot of magnesium, you've got a lot of potassium, and you look at that and you say, well, that's good. I want those things. Those are very important elements. However, you need a balance on the cation exchange sites. You need a balance with the hydrogen. Too much hydrogen is bad, not enough hydrogen is bad, and you need a balance with these other elements. So it's not necessarily good when you're up here in the high pH range. Now, 8.2 is kind of a magic number. I would guess that a lot of you, if you're dealing with sand-based systems, particularly in the Midwest and the West, you run a soil test, you're going to have an 8.2 pH. And that is because that soil, that sand, has a lot of calcium carbonate in it. And we're going to talk more about the chemistry of calcium carbonate here in a minute. It's a very important element to us in the soil. In fact, we put it on sometimes when we need it. But if you've got an excess amount of calcium carbonate, you have a soil that we term calcareous, and it's going to have an 8.2 pH. It's buffered at that point, and it's pretty much stuck there. Now, some of you, particularly if you're from the West, and maybe down here in Florida, you have very high pH soils. Yeah. 9, 10, 11. I worked in Colorado for a while, and I had some greens that had 10 and 11 pHs. Now, those are extremely high. Anybody from down here have a very high pH range? You probably do, where you've got saltwater intrusion. If you've got a lot of sodium on the cation exchange sites, that's bad. Because again, like over here, if I got a sodium on a cation exchange site, one thing, it's toxic to plants, but that means I don't have a calcium, I don't have a magnesium, and I don't have these other elements. So if you're way up there in the high range, you're way out of line on what you're going to need. You've probably all seen this table before. This is in my textbook, but it didn't originate with me. A guy named Traug way back in like the 1930s, came up with this. And what he's showing here is that here's pH 7 in the middle, and here's acidic, here's alkaline. In fact, this goes from 4 to 10. That's kind of the normal range for soils. And the wider the line up here, the more you have of an element, and the narrower the line, the less available it's going to be to plants. All right, let's look at calcium and magnesium first. Notice how up here in the 6.5, 7 range, you've got plenty of calcium. However, as you get down here in the acidic range, the line gets very narrow. Why does it get narrow? Because by definition, I've got hydrogen on the cation exchange sites. If I got a hydrogen, I don't have a calcium, I don't have a magnesium. All right, up here in the high range, you got plenty of these elements. You don't have to worry about that. Notice here at 8.2 something happens, okay? What's happening there? That is sodium. We talked about sodium a while ago. If you're up in that very high pH range, you got a lot of sodium in the cation exchange sites, and you don't have a calcium and you don't have a magnesium. So that's another area where you can run into a lot of problems. Now, you might look at this and say, well, wow, great, I want to be up here in the 7.5 to 8 range. However, there's trade-offs. Look at iron. Many of you probably have iron chlorosis problems where you got to put on some iron, and that's a pH-related thing. In the low pH range, iron's readily available. As you get above 7, it very quickly goes out of solution. The plant can't get it, and you run into iron deficiency. Manganese is another one. Look at molybdenum. Molybdenum's just the opposite. Not available down here, readily available on the top. So we need a balance. We need a happy medium there, and that's at about 6.5 to 7. That's where we have the maximum availability of these nutrients for plant growth. Now, does that mean that I can't grow grass outside of that range? And of course it doesn't. Many of you are doing this. I see people growing great grass on 8.2 pHs all over the place, but they have to adjust their fertility system. They're probably going to need some iron and maybe a micronutrient solution with a macronutrient package with a lot of these other elements in it, because they're going to run into deficiencies of some of these if they're in that high range. Now, let's say we're in the low range. We've got a 4.2, 4.4, 5, very, very low pH. What are they going to tell you to do? If you send in a soil test and you've got somebody interpreting for it, they're going to say, you've got a very low pH, you need to lime. All right, what is lime? Lime chemically is calcium carbonate, CaCO3, calcium carbonate. Now, there's another material called gypsum. We're not going to talk about gypsum today, but it's calcium sulfate, and it has a different purpose. In fact, I was just talking to Adam about this. We just finished this article. We may do one next year on lime versus gypsum. How do they differ in the soil? How does their chemistry differ? But this is lime, and it is calcium carbonate, and it is a very important material to us. If I have a low pH, I'm going to put on lime. I'm going to be putting on calcium carbonate. That's why I said if you've got a low enough pH that you're seeing a calcium deficiency, you got a lot of other problems too, and you're going to lime long before you get that reddish discoloration, and you're going to give the plant calcium. What does lime do? Lime raises pH, and that's a very important issue because I live in an area where we've got some acidic soils, we got mostly higher pH soils, but in the farming operations there, a lot of people grew up with the idea that lime is good. And I was one of those. I grew up on a farm in Iowa, and at 10 years old, if somebody would have said, what's lime, I would have known what it is. It's this white material, and they put it on the soil, and they get more corn when they put it down. Lime is good. All right? Lime is good if you have the problem that lime solves. And the problem that lime solves is a low pH. You got a lot of hydrogen on the cation exchange sites. You're going to put on lime. You're going to bring that pH up. On the other hand, I've run into many situations over the years where I'll go out and look at a turf area and they'll show me their fertility program and they're liming, but their pH is 7.5, 7.7. And I'll say, well, why are you liming? Well, lime's good. Okay, and lime is good if you have the problem that lime solves, and that is a low pH. Lime is bad if you don't have that problem. If you've already got a high pH soil and you're dumping more and more lime on it, you're antagonizing a problem that you've already got. So lime is good if you got the problem that lime solves. Lime raises pH. How does it do that? The calcium and the carbonate dissociate in the soil, and now you've got that free calcium with two positive charges on it, and each calcium can displace two hydrogens off the cation exchange sites. So they're very effective at removing hydrogen from the cation exchange sites. And what you're trying to do is restore this balance. You don't want to go too far. You don't want to raise it above 7, so you need to monitor this. But you want a good balance of calcium, magnesium, potassium, ammonium. And when you're liming, you also need to adjust the rest of your fertility program. You need to make sure that you've got the right balance on the cation exchange sites, and that means that you have to monitor this with a soil test and see what you're doing. But this is basically what we're doing. When we lime, we're putting calcium on the cation exchange sites, and if we do it right, we're going to restore that balance of the various elements. Now, back to the question on do you need calcium or do you not? Now, you can see why in that earlier slide I said calcium deficiencies are probably going to occur where you have a low CEC and a low pH. Okay, first of all, if you have a low CEC, like a sand-based system, most sand-based, or some sand-based systems, not all, you're going to have a very low cation exchange capacity, so you don't have many of these negative sites to hold the calcium in place. And if you have a low pH on top of it, that by definition means you've got a lot of hydrogen on the cation exchange sites that are there. So I don't have many sites to start with. Now I've got a hydrogen on the cation exchange site. So in that type of situation, and if you're low in calcium, you're going to have to put down some lime and build the pH up. Now, many of our soils, though, and particularly our Midwestern sands and our Western sands, have calcium carbonate as part of their parent material. They are calcium carbonate-based sands. And when you've got a calcium carbonate-based sand, you're going to have an 8.2 pH. You're going to know it. You're going to have a very high pH. And you're going to have a lot of calcium in it. So, logically, you're not going to need a lot of calcium on a calcium carbonate-based system. But that's kind of where the problem comes in with a misunderstanding of what's going on with these materials. All right, so we took on some studies a number of years ago on this because we were getting so many questions on it. I had a student, a former undergrad student named Rod St. John, who, when he graduated, went to work, this was in the 90s, for a company down in Missouri. And he sold a wide variety of different products. And he was telling me, I did a seminar for their company one time on plant nutrition. And he said, you know what, they're constantly pushing calcium. They get the young sales guys together and they say, you got to sell this calcium stuff. Why? Because we got such a high markup on it. And Rod had a pretty good background in soils, and he'd raise his hand and say, but we've got a lot of guys that have calcium carbonate-based sands. They got an 8.2 pH, and there's a lot of lime already in that soil, and they should be getting plenty of calcium. Why would we want to market them more calcium? And they say, just shut up, market the calcium. The calcium's got a high markup on it, and we make a lot of money on it, and sell it. So he'd ask again, well, what are we going to tell them? Well, tell them that the calcium carbonate in their soil is not available to plants. Okay, so they got to put more of this very expensive calcium solution down in order to improve the plant. So Rod was skeptical about this. I was very skeptical about it. And when he came back to graduate school, this is what he wanted to study. He wanted to find out more about calcium nutrition and what is right and what is wrong. Rod began in 2000 with his degree about the same time Jason was there. He remembers a lot of this work. And the first thing he started with was the question of if we take different kinds of sands, and he had a silica sand, which is very low in calcium. It's got hardly any, well, really no calcium in it at all if it's pure silica. And he used calcareous sands, those with a lot of calcium carbonate in them. He grew plants on them, and then he applied a wide variety of different calcium materials. Now, he used lime, which is the obvious one, but there were, and still are out there today, a number of very expensive calcium supplement materials. So these are a lot of times liquids, and they're very expensive materials, and they're the ones with a really high markup on them, and they'll tell you to put them down because you need more calcium, okay? So Rod did this, and he stayed on for his PhD in 2002, and there he did more work on the science of soil testing for turf, and he looked at something called calcium-magnesium ratios. This was another big issue. In fact, some of you have probably been told, look, here's your soil test, and your calcium to magnesium ratio is out of whack, and you got to spend $6,000, $7,000, $8,000 to get it back into whack, okay? Now, do you need to do that or do you need not? And that was what Rod's second study was on. Okay, in Rod's first couple of years in his master's, again, he applied a wide variety of different calcium sources, both on silica-based sands, which are very low in calcium, and calcium carbonate-based sands. And what did he find? He found that if you have a true calcium deficiency, as you do in a silica-based sand, calcium makes a difference. It's positive. We could measure a number of plant responses that said, yes, that potassium is necessary, and it is important, and you should be applying calcium to the plant. On the other hand, where we had a calcium carbonate-based system, we didn't see any response at all. We could not, we measured the calcium in the plant. We couldn't get any more calcium into the plant. The plant was getting sufficient calcium from the calcium carbonate-based sands. And that's a very important issue. It goes back to that curve of diminishing returns. If you've got enough, more and more and more is not going to do you any good. In fact, you're kind of pouring your money down the drain. So, very simple. And I kind of knew this going in, but until you've got data, nobody's going to believe it. With the data that we got from this clearly shows that if you've got a calcium carbonate-based system, the calcium carbonate is in equilibrium with the soil solution. It's got plenty of calcium. Putting more calcium down is not going to make a difference. Let's see, in calcareous soils, again, we measured the calcium in the plant. He couldn't get any more in. Did it make a difference which calcium he was using? Okay, and that was a very important issue because lime's cheap. You can buy lime very inexpensively, and lime is very effective, as he's shown. We already knew that. The question was, were these very expensive calcium-based solutions going to give you something for your money? And the answer was no. Liming did as much good as materials that were extremely expensive. I'm going to talk more about these materials here in a minute, but a common thing that I see going on in the industry is that you'll get products that are spiked with nitrogen. They're spiked with urea. Urea is a great nitrogen fertilizer material. It's very inexpensive. You can buy a pound of nitrogen from urea for about 60 to 65 cents a pound. Okay, and what they'll do with a lot of these solutions, and I've got another talk on biostimulants. Do biostimulants work? Well, it depends. And what you'll see is that there's a lot of products out there called biostimulants, and what they'll do is throw a little bit of urea in it. And they definitely do this with a calcium solution. So they were marketing these calcium solutions at enormous cost. In fact, I did some math on it when Rod was there, and we'd find these different calcium solutions for sale in the Midwest. And first of all, what we were finding was that the calcium wasn't doing any good at all. The calcium, if you had enough calcium, more calcium wasn't going to make a difference. However, if they spiked it with 15, 20 cents worth of urea, you put it on the turf, you're going to get a green response. And that's one of the things that's going on. They'll say, here, try it. They'll do this to the golf course superintendents. Here, put a strip out on your green with this calcium material that we've got and see if it doesn't work. And they get this beautiful green response where they put it down, but it's not the calcium. It is the urea. It's the nitrogen that's giving them the green response. Now, we looked at the cost of these things, and we did some comparative analysis on what you're paying per pound nitrogen. Okay, and first of all, I was seeing $50 to $60 per pound nitrogen. So that nitrogen you could buy for 60 cents, you're now paying, and you're not getting anything out of the calcium. The only green up response you're getting is from the urea, but you're spending $50 per pound on the urea. And then in Kansas City, I saw the most extreme one a few years ago, $100 for a pound of nitrogen in this solution. And what they're telling you is, oh, it's a calcium-based nutritional supplement and you need it for your turf. You're going to get a little response, but you're going to get that response from that few cents worth of urea and not from the calcium. Now, how do we know that? When we put out these studies, we have to balance that very carefully. We have to, and we'll test the solutions. And when people submitted these solutions to us for evaluation, we didn't listen to them as to what was in them. A lot of times they won't tell you that there's nitrogen in them. You've got to test them separately. We'd find out how much nitrogen was in it, and then we would do an apples to apples, oranges to oranges test where we would put out increasing amounts of calcium with these, but we balanced the nitrogen out. So all the plots were getting the same nitrogen, and the only difference was the calcium. And when you do that, and you've got enough calcium, you're not going to see an additional benefit from the calcium. It's from the nitrogen. So kind of be careful with what you're doing. And like I said, in his studies where you did need calcium, and there were situations where you did need calcium, it was the cheaper materials that did just as well as anything else. So if I can spend $1.50 to fix a problem, or I can spend $80 to fix the problem, I'm going to take the $1.50, and that's going to be the line. Let's see. Rod's PhD work, he got into some of the finer points on soil testing, and what we found out is that in a lot of cases, we're not doing things right, particularly at the calcareous sands that many of you have. Our soil tests weren't made for that. They were made for clay loam soils, and trying to interpret those are very difficult. So he did a lot of work on that. And then he looked specifically at this calcium to magnesium ratio thing. And we still get a lot of questions about that. They'll call up and say, well, I had the fertilizer company do a soil test for me, And they came out and they laid it on the desk and they said, here, look at this. You've got a calcium to magnesium ratio that's out of whack, and you need to fix that calcium to magnesium ratio, and here's what you need to buy to do it. Be very skeptical when you hear that. In Rod's studies, he varied the calcium and the magnesium ratios on the cation exchange sites through a very wide range, and what he found was that it didn't make a lot of difference. Now, you can get true imbalances. If you don't have enough magnesium or you got too much magnesium, that can be a problem, but it's at the extremes. Through most of the mid-range, your calcium to magnesium ratio is not going to make any difference. So if somebody's trying to sell you something very expensive based on your calcium to magnesium ratio, get a second opinion. Run a soil test through your university or through an independent consultant who's not trying to sell you something, and let them interpret that for you. Because a lot of times there's misinformation going out there, and it's very expensive misinformation. So back on that curve of diminishing returns, and back to the original question, do I need calcium? What's the deal here? If you've got enough calcium, you don't need more calcium. Okay, so if you have a calcareous-based sand, you've got a high pH sand, you don't need any supplement of calcium because you're getting enough calcium from the calcium carbonate in that sand-based media that you're out here. So, and can you do harm if you get too much? Yes, you can put down too much. You can saturate the cation exchange sites with calcium at the expense of magnesium, at the expense of potassium. So you don't want to put on something you don't need, and you don't want to spend dollars to do that. If you have a true calcium deficiency, you're going to get a response, and that's going to be in like a silica sand, low pH, low cation exchange capacity. You're going to see a response from the calcium. Do you need to spend $70, $80, $90 per gallon on a calcium supplement? No, because you can put down lime. There's other calcium sources. There's dolomite, which is a calcium magnesium based material, which is very effective if you're low in both, and you can solve that problem very inexpensively and get it up into this range. Back again on the curve of diminishing returns, and let me leave you with this today, and then we'll do a little discussion. If you have enough, more is not going to help, and that goes through all through life. Like I said, vitamin D. If you got enough, more vitamin D is not going to help. It's probably going to hurt. So only where you have the deficiency should you be using these. The calcium and magnesium ratios, you can vary those through a very wide range and still grow really good turf. You don't need to spend a lot of money balancing out your calcium-magnesium ratio. And that's basically, I've summarized it here. Calcium, if you don't need it, don't use it. If you need it, use it, but use inexpensive materials.